Hi, welcome to a class called The Physics of Harmony and Keyboard Tuning and Temperament as well. So we're going to start by listening to a few things on this CD player. And the first two little snippets are of a pipe organ that has been tuned in an old historic temperament. And actually the first two, one of them's mean tone, the second one is in Werkmeister 3 temperament. So let's listen to these samples. A little later, in the Baroque period, circulating well temperaments were introduced to the keyboards. And what I'd like to do is play you a short sample of one of those. For my third example of harmony, let's go to the human voice. Probably the kind of ensemble that likes to key into harmony the best would be barbershop singing. And so I've got a couple of examples from the barbershop repertoire.
And the walls came tumbling down, the walls came tumbling down. Yeah. Judge made the battle of Jericho, around Jericho, South Jericho. Yeah. Judge made the battle of Jericho when the walls came tumbling down. Judge made the battle of Jericho, Jericho. What a morning when Judge made the battle of Jericho. When the walls came tumbling, 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 the mighty walls around Jericho came down. Those mighty walls came down, tumbling down. Let me tell you, those walls came tumbling down. It ain't slow, it ain't too slow, but oh, that glory, hallelujah, sway, 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 while they play. Make somebody wanna stay, around all day, hush my mouth, that's the sound from Rampart Street, Rampart Street, hush my mouth, oh my Lord, that's the South Rampart Street. Oh, I love the beat. The beat of that Rampart Street parade, the shaking it, the breaking it, the swaying it. I said I still hear the beat, the South Rampart Street parade.
So I'd now like to introduce Dan to you. Dan is my student today, and I'm going to ask Dan, while he's been listening to this music, what he's thinking about with this question, what is harmony? And I'll just write down some thoughts. So Dan, thinking of any definitions that might work for harmony?
I mean, right off the bat, I'd say harmony really is like any like combination of notes that sounds, well, that doesn't sound dissonant. That sounds pleasant to the ear.
I'm going to say sounds. Did you say notes? Should I say notes too? Because
yeah,
you're thinking of music?
Yeah.
So that would be good. And I think, did you use the word pleasing?
Yeah.
Yeah, that's a great word. I like that definition a lot. Anything else come to mind?
Well, I mean, I know what it isn't because I don't think that something sounds harmonious if it's like dissonant. You know, if it like if the notes feel like if the sounds feel like they're almost like fighting each other. It's not the first thing I think of when I think of harmony.
Right, and I like the idea of fighting, because we might want to come back to that idea. So I'll put down fighting sounds, because I was thinking of that too. All right. Anything else I could add on the side?
I think that covers it.
Yeah, okay, great. The only thing I want to do is add a little bit of math to this, because when we're talking about sounds or notes, we're also talking about frequencies, and when we're talking about frequencies, then we're talking about numbers, because it's the number of cycles per second of the sound as it's being produced. And that's what vibrates our eardrum and eventually tells our brain, you know, what it is we're hearing. So if you don't mind, we're going to need to do some math in the next hour or so, and that's why I've supplied you with a scientific calculator and a dollar store calculator, so you can use whatever you want, whenever you want, and that'd be great if you would try. I'll give you some things to do in a little bit. All right, so I'm going to go over to my powerless, pointless presentation over here, and I'm not very good with electronic stuff, so I put my slides on poster boards. So I'm going to give you this mathematic definition: combinations of pitches whose frequencies are related by whole number ratios. Now, you know, we didn't talk about the math yet, but this is what it's going to take to make sounds that come to our ear and are pleasing to us. So we're going to need frequencies that have a ratio of 2 to 1, 3 to 2, 4 to 3, 5 to 4. When they are simple ratios like that, and you're listening to them at the same time, that's when you're going to say they're harmonious or part of harmony. Now, the other thing I'd like to do, and the reason why I have a lot of things set up here, is I'd like to come up with a way that we can visualize harmony. So, Dan, I'm going to need your help for the first demonstration.
Okay.
This looks like string, but it's actually bungee string. Okay, it's springy. So Dan, if you could take the end of that and go to maybe over that way. We want to stretch out here about this far. That's good. And if you'll just hold it up, and then I'm going to give it some tension, so don't let go.
Yeah.
It would be fun if you did, but I won't do that. All right, so I've got some tension on here, maybe too much. I want just a little bit. All right. And if I just wave it around, a bunch of things might happen, but if I find just the right frequency, I can make it go up and down, kind of like reminds me of a jump rope a little bit. And so when I do that, I found what's called the fundamental frequency, the first frequency I can do to make something called standing waves. So I wave it here, the wave goes to Dan and reflects back to me from his hand. And if I get just the right frequency, it comes back with this nice loop. All right, I like to call it a loopy. Now I'm going to double my frequency. Watch what happens. Doing this right? I don't think I have it quite right. That's one. I want two.
There you go.
There.
All right, 2 loopies. I think that I doubled my frequency, because according to my rules, that's probably what I need to do. And if I could triple my frequency, I might be able to get 3. But I think it's too hard for my arm to do that. So we're going to move to this apparatus on the table that will allow us to do the same kinds of things and have a lot of numbers that we can work with. So this was just to sort of give you the idea of what we're about to do. But visualizing harmony with a bungee string vibrating, I think is a great way, as long as you can build up standing waves. And standing waves are these loops that I'm talking about. And if I use the term loopy, please excuse me. It's just more fun. All right, so the fundamental frequency that I was trying to show you would just be one loop going back and forth between one end and the other. And if I double the frequency, I should be able to get 2 loops. So let's see if that really works in a way that we can measure it using some equipment that I brought over here. All right, so I'm going to turn on this function generator. And what this function generator does is it tells this vibrating machine over here what to do. Now the vibrating machine is not only going to vibrate this post up and down. Oops, I made the string come off. Let me put it back on. But it's also going to make a tone if the frequency is high enough for us to hear, because it's got speaker material in it. So I don't know if you could see, but there's kind of a yellowy orange colored part to it, and that's the speaker part. Okay, so I've got this bungee string. I've stretched it out. I've made it, just for the heck of it, I made it about 1.5 meters from here to here. It seemed like a good distance to fit with our backdrop. So I've got some meter sticks here, and maybe Dan later on I might have you help measure some stuff. So we'll keep the meter sticks right there. And then I put a 200-gram mass as a weight on the end to keep a certain tension. So I tried it out earlier and it seemed to work pretty well. So hopefully it will. When I turn on this function generator, it defaults to 1,000 hertz, 1,000 cycles per second, which is a pretty high-pitched, annoying sound. It's not very loud, but you can probably hear it. I'm going to bring it way down because that's way too high of a frequency to even notice what's going on in the string. By the way, that's close to 440 hertz, that tuning note that the orchestra uses, just in case you're wondering where we're at.
There we go.
Okay, I'm down to 3 cycles per second. If you look at the vibrating part right now, it's going up and down 3 times a second. But and we're not getting a standing wave. It's just too slow of a frequency to get a standing wave. So let's bring it up and see if we can get a standing wave at a frequency that this will tell us. This will tell us what it is. I just have to, no, 13th, not what I want. All right, so here's 4 cycles per second, 5 cycles per second, 6 cycles per second, 7. Okay, we're getting something that might be getting close here. 7.5. Oh, I like that. Now I went up to 8. Now is it getting worse? like less
Yeah, it's a little bit less.
less bounce. Okay, so I think it was between 7 and 8. Let's see if we can hone in on the frequency that would work best for this. Okay, so 7.9, 7.8, 7.7, 7.6, 7.5. Right there in the middle is really good, and we call that distance in the middle the amplitude. The distance from where it would be if there was no wave to either the highest or lowest point. So I think we're getting a pretty darn good amplitude at 7.5 cycles per second, or hertz. If you're looking at the little screen here, it says Hz, and it's the same thing as cycles per second.
Okay.
All right, so we've got our fundamental frequency for this given bungee string and this given distance and tension. So given those initial conditions, 7.5 cycles per second is our fundamental frequency. So Dan, I want to try to get 2 loops on here, and from what I was telling you before, what frequency do you think I should bring this up to?
Oh, probably 15.
Yeah, let's go up to 15. Okay, so we
It's
got
doubling.
8, 9, 10, 11, 12, 13, 14, 14.5, 6, 7, 8, 9, 15. Whoa! 2 loopies. They look great. All right, you were right. I mean, I can go a little bit past it. Let me go a little past it. Okay, here's 16. See, it got worse. It might have gotten a little bit better, but I think it's still really good around 15. So I'm going to hold it there. Dan, would you go up to the table and see if you can figure out how long one of these loops is?
Okay.
So I want you to measure from, I don't even think you need to move the meter stick, but if you're looking at the end, it's pretty much where the wheel is, and that's the end of the string. And then this point in the middle is called a node, and what's happening is as the wave is going back and forth, reflecting back and forth, it's canceling itself out in the middle. So right there is the end of the loop. So can you tell me about how many centimeters we're at with a loop?
It's about 75.
Yeah.
Yeah.
And that would make sense, right? Because the whole thing is 1.5 meters. And do the loops look about the same size?
Yeah, they do.
Yeah. And that's just the way it is. They divide exactly in half. The string will divide exactly in half. And we have 2 loops that are each 75 centimeters. Great. Well, let's have fun and try to get 3 loops on here, okay? So what frequency should I bring this up to get 3 loops? Do you have a good idea?
Probably about 22-ish, somewhere around there.
All right, let's go up to around 22 and find out. How did you get that number, by the way? You want to tell me?
I kind of just did like a rough, I tried to multiply our fundamental frequency, 7.5, by 3.
Yes.
Yeah.
That's exactly what you should do. Great.
Which
is actually
slightly more than
22 and a half. Yeah.
22
Okay.
and a half, yeah.
So we're up to 20 here. Not good yet. 21, 22.3, 22.4, 22.5. Hey, I'm seeing 3 nice loops. Yeah, that's excellent. So I think you nailed it. How about measuring one of those loops and see about where the node point is for the first loop?
It's 51. Close to
Yeah.
51, yeah.
Okay.
1.5.
But, probably, if the whole thing really is 1.5 meters, it's probably about 0.5 meter, right?
Yeah.
Cool. All right, we could try the 4th, by the way, that's called the 3rd harmonic. We
Okay.
could try the 4th harmonic. What do you think that would be?
30, I think.
Yeah,
Yeah.
I think so too. Because 7.5 times 4 is 30. So here we go. 25, 26, 27, 28, 29.567. 8, 9. There it is, 30. Yeah, not bad. How long is one of these loops?
It's around It's around like 39 centimeters, 38 and a half, something like that. But
Okay. And would that be a quarter of 1.5?
no, it should be 25. Well, no.
Now, wait a minute. Let's think about this. We got
No.
1.5. You can use your calculator.
Yeah, that's right.
Go ahead, use your calculator. Just to make sure we're doing this right. So I'm just curious. What's 1.5 divided by 4? Wouldn't that tell us what it should be?
Oh yeah, 37.5.
Oh, yeah. Well, we're good. All right, and we're just gonna do one more. I think you're starting to get the idea. So what shall I bring the frequency up to get 5 loopies?
This should be.
You got the calculator if you want to
Yeah.
use it. It's up to you.
Let me just do that. 37.5.
32, 33, 34, 35, 36, 37.345. Actually, trying to figure out if it is a little bit better at 37.8. But anyway, we are getting 5 loops though. 1, 2, yeah. And how long are each of these?
Around 31 centimeters.
Should they be exactly 30? 3 times 5, 1.5. I think they should be exactly 30, right?
Yeah.
Okay. So yeah, I mean, I'm not, we didn't do everything to a huge number of significant figures, but we've definitely got it pretty close. So that's great. What you've seen is a harmonic series visually on a bungee string, and we've now got the 5th harmonic on here, and it's 5 times the original frequency. So, okay, great, that's a lot of science, but we haven't really heard any sound because these frequencies are really low, and even though we should be able to hear 37 or 38 cycles per second, it's pretty low, and it has to be pretty high in volume to hear well. That's one of the reasons why bass speakers are so big, is because our ears aren't really sensitive in the bass range particularly, so you're not really hearing that yet. But at least you can see what's going on. Now, I'd like to try a little experiment. I'd like to bring down the garage door and make it as dark as we can in here, because if we try having a strobe light on here, it might be fun to see what's happening there. So let's try that. So we're in the darkness here, or pretty dark, and I've got a strobe light on the bungee cord now. It's still got 5 loopies, but if I adjust the speed of the strobe light just right, I think it's got to be the other way. All right, slow it down to about there. I can make a standing wave look like it's standing still, because I'm flashing it at the same frequency as the vibrating machine at the end. So it's kind of cool to see it that way too. Okay, we'll bring up the lights again. So now what we're going to do is we're going to calculate some harmonic frequencies, but we're going to use numbers that are more useful to us so we can relate it to music. Because frequencies like we were looking at with this bungee cord were really low and not the same frequencies that we're often listening to when we listen to music. So I'm going to turn this off. I think we can now. And I'm going to let Dan see this key here. According to the rule that I told you that harmonic frequencies are whole number ratios to other frequencies, so like the octave should be 2 to 1, the perfect fifth should be 3 to 2, that sort of thing. What I'd like to do is, using this key, I'd like to come up with frequencies for notes between A220 and A440. I've chosen these frequencies because most people have heard of 440 hertz as the tuning note for the orchestra. It's the A above middle C. So you're thinking about a piano. That would be the note that the oboe or the violin is playing when they're tuning up the orchestra, generally speaking. It's a standard. And according to this, an octave below that would be a 2-to-1 ratio, would be 220 hertz. So if we think about the A below middle C and the A above middle C, I put them on this whiteboard. But now what I'd like to do is have us use the rules of harmony to figure out at least some of the other frequencies that we should have when we're tuning all the notes of the scale. And I put all the chromatic notes in here. We won't do them all this way, but we'll do some of them. So I've already done the 2-to-1. The 220 times 2 is 440. But Dan, you got to help me out here. I want to do the next one, which would be the perfect fifth. Now, let's think about this. What's the perfect fifth above an A on a keyboard or when you're playing an instrument? Are you familiar with that?
Would it be E?
It would be E. Awesome. All right, so let's figure out what the frequency should be for E according to the rules of harmony and using the 3 halves or 1.5 ratio. So Dan, I'm going to have you do that and then I will write it down.
It's 330 hertz.
Good. All right, let's try the next one. The perfect fourth above A220 would be what note?
Would it be D?
Mm-hmm. And let's find out the frequency of that. So you want to, well, you could multiply by 4 and divide by 3, or you could multiply by 1.333, as many 3's as you can type in, might as well. And what do you get?
I get 293.3 repeating hertz. You want to just call that 293?
293. I'll go one more place.
Okay.
Point what?
It would be 0.3 then.
0.3. All right. Yeah, we'll just go to the one more place. Oh, that technically then this would be 330.0 if we're going to really do significant
Yeah.
figures, right?
Yeah.
Good. Okay. So we'll go. Calculator should be able to handle that. All right. Let's talk about major thirds. How about major third above A220? It says it's a 5-to-4 ratio.
That would be C.
Now, when you're talking about A, key of A, it's not C, it's C sharp.
C sharp. Okay.
Yeah.
All right.
All right, but let's find out what the frequency for C sharp should be. Let me know when you got it.
That would be 275.0 hertz.
Okay, so that one came out nice. Yeah, and all of these are cycles per second or hertz, so I'll try to be good with my units. All right, let's do the minor third. So the minor third sounds best, sounds correct, when it is a 6-to-5 ratio, or 1.2 times greater than the original frequency. And we're using our original frequency right now to be 220 hertz, that A, below middle C. So what do we think the C natural should be?
It would be 264 hertz. Well, 0.0 hertz.
So that one came out nice too, though, right?
Yep.
Good. All right. There's only one other one I think we're going to do right now, and it's this dominant seventh. Now, when I'm talking about the dominant seventh, I'm talking about when you hear da 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 da, that note there, and it's a very common note in barbershop harmony. So anyway, dominant seventh, I'm going to call it, is supposed to be a ratio 7 to 4 above, if it's going to sound good to us. Or you could multiply 220 by 1.75, and we got to figure out what note that is, by the way, so I can write it in the right spot on my chart. So if you could help me out with that, we'll fill that, be our last one to fill in with the harmony right now.
Now would that be G?
It would be G, good. And what are you getting for the frequency?
.385 hertz.
So it came out nice.
Yep.
All right, good. I'm not going to worry about the other ones right now. Actually, I don't think I'll worry about them at all. But we are going to fill in another part on this chart a little bit later. So anyway, when we hear these two frequencies together, like A220 and C264, or A220 and C sharp 275, these should sound really nice to us and really in tune and pleasing to our ear. But why? I wonder why, or what it is about those two notes together that will sound so harmonious and pleasing. Maybe might be kind of fun to, at this point, put this computer on 220 hertz, and then we can try some of these notes on here quite easily, and listen to them together and see if there's any adjectives or whatever to come up with to try to describe why it sounds good. So I'm going to try that. So what we have here is we have that A220. It's just a constant A220, and I'm putting this speaker over here at 264 so we can hear what a minor third should sound like very purely. Let's try the major third at 275. I don't know. What do you think? Sound pretty good?
Yeah.
Do, re, mi, right? Okay, let's try, it's so easy to do this. Let's try 293.3. So that's a fourth. And then we would go to 330 for the fifth. Would be do to so. We're getting there. I just think it's kind of fun to do this. but I think the word we want here is beats. Because when I bring this down, let me just bring it down to like, instead of 330, let's bring it down to like 329.0. Okay, so let me just do that. I think we're getting about a beat per second. I'm going to bring it to 328.0. Actually, it's changing, isn't it?
Yeah.
So something is not constant, and I don't know whether it's my computer or this, but it's about 2 beats per second, and it should be, because turns out if you subtract, the number that you're listening to from what the ideal would be, in this case 2 hertz, that should be the beat rate.
Okay.
Yeah. So you get the idea there. I'm going to go just up to that 385. I'm going to try to make this go a little quicker by moving the 385. That would sound a little weird to you?
I don't know how to describe it, but yeah.
But there aren't any beats.
No.
Huh. Something about it, just, I don't know. When I hear this one, my ears perk up. But we could talk about why my ears perk up later. I don't know if yours do. Okay, let's turn this off too for now. Well, true harmony should really sound beatless. And so if we can eliminate those fighting sounds to us, which do have to do with dissonance, when we can eliminate them, we've eliminated all the beats, and then should sound really, really nicely in tune and harmonic. Sounds good. All right, now, what we could do right now, I don't know if you want to do this, but we could try to, with our voices, sing what we were doing with the machines. So we could use our ears to sing in. Might be the easiest, if I put this, I don't know if this will come back on. That's a pretty good note for anybody to sing. It's just close to middle C. It's that A right below. So I don't know if you feel like doing this, but I'm going to see right now if I can sing the C sharp or the major third, and I'm going to try to use a straight tone and see if I can get it to sound beatless. I don't know if I can do that, but I'm going to try. I'm going to use the do, re, mi. Do, re, mi, mi. I might do this in falsetto. Maybe a little louder. I don't know if I can do it with chest voice and still be steady. Want to try one? I don't know. I'm not going to embarrass you if you don't want to. You don't have to.
I could try the same one.
Yeah, go ahead. Sounds awesome. I want you to know you sang the one below. So what you were singing was whatever half of that is.
Yeah, okay.
But it also can work really nicely because you end up getting beats or not beats.
Yeah.
With that interval. Instead of being a major third, it could be a major, a sixth, the sixth below instead of the third above. So it sounds good. Cool. All right. We can try another one. I'll try the D. So do, re, mi, fa. No, here comes the bride. I'm thinking of Here Comes the Bride. Fa. If you could do the low one for me, that would be cool. You want to try?
Sure. Fa.
the E. And why don't you try the low one? Yep. Cool.
Yeah.
That's fun. All right. So, thanks for doing that with me. A lot of people don't have the guts to do it. All right. So now that we've tried making, like really zeroing in on straight tone, pure harmony so we can try to get rid of all the beats, then what do you think gets in the way of true harmony? Can you think of some things that might come up in music that makes it really hard for us to get true harmony? We might get close, but we either don't hit our pitches quite right, or it's really hard to. I don't know, any thoughts going through your head? Maybe some things that I've alluded to before, I don't know. I mean, I actually do have two things in mind, which I will reveal eventually, but I wondered if you had them in your mind yet.
I mean, to be honest, nothing like specific, but I mean, like, when, I play guitar. I know that when I play like my guitar, like sometimes like the temperature can like affect how, it can affect the tension of the strings, and that could make it, tough to, unless like you like tune it again, it'll make it, tough to get actual harmony out of it.
Sure. Okay, good. I'm going to throw out another word. Opera. What do you think of when you think of opera singers?
Well, I think of, I mean, like they sustain notes for quite a long time.
That's true. They're great singers. But would you say that opera music is about focusing on harmony or something else?
I'm not too sure.
Well, I mean, when you think about it, opera is a very dramatic
Yeah.
form of art, and when you hear most opera singers, at least in the more modern or romantic, period and sooner operas, the voice tends to be very full of vibrato, right?
Okay, yeah, that's right.
Right? I mean, that's just part of the style.
I was going to say dynamics, but yeah,
I was thinking of that, and how can you listen for no beats if there's vibrato?
Yeah, that's true.
So that's number one. And then the other thing I have to talk about is keyboards. Now, when I do this class for barbershop singers, I'm probably nearly done because they really, really try not to use keyboards. They'll bring a pitch pipe to get their first pitches, and then they just try to sing without any accompaniment. But as I tried to allude to in the beginning, too, by playing a couple of short organ pieces, or bits of organ pieces, we have problems with keyboards. And even if you are a barbershop singer, I think this part is still worth learning because, and certainly if you're a keyboard player, this part is worth learning. But that is because there's a problem with keyboards and tuning. And it's very, very hard to get all the pitches on a keyboard to be completely harmonically in tune. So those are the two things I wanted to bring up. The vibrato thing, I don't really think there's too much more to say. And I'm not trying to pick on opera singers because I think that vibrato is a great stylistic feature of the voice that can really bring out the drama in that music. But it isn't going to help with trying to focus on harmony. So, now let's go to the keyboard. So I just want to spend the rest of the time on the keyboard issue. So around 1850, most musicians and keyboard players decided that equal temperament would be the way to go for most keyboards, whether it be a clavichord, an organ, or a piano, or a harpsichord, certainly the piano. And this is where you make all of the half steps the same. So musically, they're the same in that I could play in any key and the relationships mathematically would be the same. And it's great if I need a piece transposed up or down. Maybe it's a little too high for me, so we bring the piece down a whole step or more, and then I can just sing it as if I sang it at the other key, and it's more comfortable for me. But the thing is, I want to point out to you that equal temperament does not follow the rules of harmony that we just learned. So part of the reason is that the math involved in tuning a keyboard in equal temperament is completely different than this math we were using for harmony. You don't use the idea of whole number ratios like 2 to 1 and 3 to 2 and 4 to 3. What you do is you take, let's talk about our 220 hertz to 440 hertz. You take those two frequencies and you got to figure out a way to divide up all of the half steps that we know of on a keyboard, there's 12 of them, so that when you're all done you end up at 440, and they have to all musically come out the same. But you can't just divide it by, like, divide 220 by 12, because the problem with that is, then what we would have is, if we went the other way, 220 divided by 12, and we went down, we'd be at 0, instead of a 110, and the next octave down would be 110. So the problem, it's a really tricky math problem, because each octave is a doubling of the frequency, but that is not a linear scale, it's a curved scale, so logarithmic or whatever the word is for that, but we can't just divide by 12. So what do? We take the 12th root of 2. Now, that's not something we do very often, but it works great for equal temperament frequencies. Dan, do you know how to get the 12th root of 2 on a calculator?
Let me see if I do.
If you don't, I'll tell you, because I know some tricks to get it quickly, but maybe you know a good way to do it.
I think I'll actually need help with this one.
All right, well, another way of writing it is 2 to the 1/12th power.
Okay.
So if you were to go 2 on that graphing calculator, and then just use the little caret button,
Yep.
and then in parentheses go 1 divided by 12, close the parentheses, I think you will get this magic number. Did you?
Yep.
What is it?
How many digits are we doing?
Well, yeah, just I want to make sure you got the right number. What is it?
1.059, yeah.
That's the number, okay.
All right.
Yeah, and it goes on and on. It's a crazy number.
Yeah.
All right, so we're going to try using this mathematic technique to figure out what the frequencies would be if we were going to tune a keyboard using equal temperament. So what I'd like you to do is, maybe you might want to use that little dollar store calculator and put 1.059, whatever the other,
For
as many as
5.
you want to put in there, but give me like maybe 6 significant figures or something like that.
Yeah.
And you could put that in memory plus, and then you'll have it, you can recall it, and we can try this pretty quickly. So here's what you're going to do for me. I want you to type in 220 times memory recall,
Okay.
and that's that 1.059 whatever, and you will give me the frequency for A sharp.
Yeah.
So what is it?
It's 233.08 hertz, yeah.
Okay, and I think 4 or 5 significant figures will be fine. All right, now don't erase that number. Keep it there. You can keep all those figures that are on the calculator.
Yeah.
And then just multiply it by memory recall again. If you just keep doing this, it should keep giving us the next number. So try it again, and what are we getting?
246.94 hertz.
Great. Do it again, and we should have our minor third pitch.
This one's 261.62 hertz.
0.62?
Yep.
All right, now I just wanted to pause for a moment. Take a look. We are not very close to the harmonic pitch for the minor third, are we?
No.
No. Okay, let's do it again and see how about the major third? How's that come out?
277.18 hertz.
So what I'm noticing here is that in equal temperament, the major third is too high and the minor third is too low. Okay, let's go on and find out about the perfect fourth.
This one's going to be 293.66 hertz.
0.66?
Yep.
Well, that one isn't horrible. Okay, let's see what D sharp would be.
311.12 hertz.
All right, let's see how the perfect fifth comes out.
329.62 hertz.
Yeah, this is interesting. It's a little bit off, but it's only about as far off as the fourth. But the fourth was a little high, and the fifth in equal temperament is a little bit low. Okay.
Next one is 349.22 hertz.
0.22.
Mm-hmm.
All right. And now let's do the F sharp.
369.98 hertz.
All right. G, please.
391.98 hertz.
Wait a minute. Say that again?
Yep, 0.98.
Oh my goodness. Check this out. This is so much higher,
Yeah.
right?
Yep.
Wow. No, remember I told you that one just sounded a little weird to me,
Yeah.
and you could probably see why it might sound weird to people. Okay,
Yeah.
next one.
415.29 hertz.
One more time, please.
All right. This one's 439.98 hertz.
Which, if we round it, right?
It is 440, yeah.
Yeah, we really are back to where we are. And that's the one interval in equal temperament that you can count on as fine, is the octave. It's the only one that's really fine according to the rules of harmony. So, yeah, this is the problem with equal temperament. The fourths and the fifths aren't bad. You can live with those. But the major thirds and the minor thirds are pretty bad. And this dominant seventh thing that barbershoppers love, whoa, way different, way different. So you might be interested in hearing what 220 to 392 sounds like compared to 385. You know, that one might, or maybe I think we should even try like the major and minor thirds too. So let's try those three pitches to see if we notice the difference between what a keyboard that's equally tempered would play versus what pure harmony would ask us to sing, or you know,
Yeah.
here on a keyboard if you tune it that way. All right, so go back here. So we have our 220 hertz here again, and I still have the function generator at 385, which was our harmonic dominant seventh here. That's what it should be. And here's what a equally tuned keyboard would be. playing the A, and I want to go up and play the G above it, you're going to hear that. Sounds okay, right? Because we're used to it. But, according to this, that's what it's really supposed to be. And when I started singing barbershop, it took a long time to get used to letting that note fall until it kind of locked in my ear. All right, well, let's take a look at the major third. That one is quite a bit too high, so let's try 277 here. So, do, re, mi. This is your typical keyboard C sharp, but this is what it should be. Do, re.
Yeah, I see. It sounds
Yeah.
better. Yeah.
And listen to this. I'm going to bring it back up to 77. It's a little hard to hear the maybe the beats, because it would be more in the overtones, maybe some of the other things that are being formed by the speakers and the sound. But anyway, that's the difference. And I'd like to. Okay. And while we're at it, we'll just check the minor third. So what we would expect. Maybe I better bring this over. All right. So what we should be hearing is 264, so I'll go back and refresh that. Okay, so that would be a pure minor third. But this is what we get with today's tuning. 261.62. All right. Okay, Dan and I are back with the bungee cord one more time, and I just thought it might be kind of fun to show you, well, you know, I was trying to show you with the machinery I brought, the first harmonic, and then second harmonic, getting two loops and all that. But I wonder what would happen if I took this saber saw and tried doing this. And what I'm going to ask Dan to do is figure out which harmonic this is, and if you know a jazz trumpet player, you might think about how when they're squealing away on their high notes, how it might be similar to this. Do you have a harmonic for me?
No, I'm trying to.
Well, what were you trying to do?
I was trying to count the amount of notes.
I just wanted you to count the number of loopies.
Oh, okay.
Let's
All
try
right.
it one more time. Let's see
Let's
if
do
we
it
can find it out. Because remember, the one loopy waveform is the fundamental or first harmonic.
Yeah.
And the two loopy one is the second harmonic. So
Yeah.
all you gotta do is count how many of these loops.
Yeah.
And I think this is pretty constant once it gets going.
The 20th harmonic, or?
I have no idea. I just wanted
Oh,
to
okay,
count.
okay. I might have missed one.
Whatever you got, it was
Yeah.
about 20. Yep.
About 20, yeah.
Yeah. And I was thinking about how when jazz trumpeters are playing high notes and they're riffing a bunch of really high notes together, they don't even need to use their valves because between 20 loops and 19, or even between, let's say, 13 and 14, or something like that, it's the wavelength difference and the pitch difference is so small that it ends up being like half steps, and you don't really need to change the length of the tube. We didn't change the length of the string, and we got that many. So that's a parallel I thought of there. And thinking of musical instruments, I've got one right here. Do you know what this is?
I don't know what it's called, but I've seen it before.
Yeah. Well, sometimes it's called a bluegill tube, or a lasso de amore, or I don't know, freaka tube. Anyway, it's interesting that when you whirl them around, the air cutting across the end forms kind of like blowing over a Coke bottle, and it forms tones. But if you go faster, now you can try it. It's fun. Let's see how many notes you can get on it. Okay, that's probably the lowest one. Okay, a little faster. Can you do one more? Okay. Oh, got one more. Cool. So, did you notice what the intervals were of the pitches? Because they weren't a scale. They weren't like do, re, mi.
Are they thirds?
Well, there was a third, a minor third, and a major third. You got them both. What you were doing, I think, was going up the harmonic series.
No.
Let's think about this. Because remember that chart I showed you where you were multiplying the frequencies? I think it was, I'm trying to remember where I put that one. This one here. So, an octave, like if you take some note and you go up one octave, it's a 2-to-1 ratio. And that would be like going from one loop to 2 loops. So you would double the frequency and you would cut the wavelength in half. Or the loop length would have been in half too. Okay, if you were hearing a perfect fifth, it would be like the ratio of 3 to 2. So 3, it could be a frequency of 3 to 2, or it could be a wavelength of 2 to 3, that relationship. Either one, frequency and wavelength are inverse, but you still get these whole number ratio types of things. So the second harmonic is a perfect fifth above, well, okay, so, sorry. The fundamental is going to, if you have a fundamental, and then you go up to the next harmonic, its second harmonic will be an octave, the next harmonic will be a fifth, it'll be the third harmonic, the fourth harmonic will be a fourth above that, or 2 octaves above the original frequency, and then the fifth harmonic will be a major third above that. So let's figure out if we can get the first harmonic and the second harmonic, in an order on this. So listen to this. There's my lowest note, it's not very loud. Or how far apart are they? Are they an octave apart?
No, they're not.
No. Are they a perfect fifth apart? Yeah. So, the lowest note I'm able to get on this bluegill tube is the second harmonic. And the next note is the third harmonic. Second harmonic, third harmonic, fourth. So that was the perfect fourth. Here comes the bride.
Okay.
That's the perfect fourth. Okay. Now, fa, do, re, mi should be the next one. And you got that one, I know you did. So that would be the major third. And then, see if we can get the minor third above that. Yep, you even hit that note too. So we can get all the way up to about the fifth harmonic, maybe sometimes even the sixth harmonic. I don't want it, even once in a while heard a 7th harmonic out here. But if you start going crazy, sometimes the plastic will break and then your blue little tube changes key and it gets too short and it's just really sad. But as a prize for being the greatest student today, you are going to be able to keep this blue little tube.
Really? Well, thank you.
You bet. All right, now I have a little more listening to add to my presentation. So I'd like to explain what I have here on my boombox to finish off. So a couple more things on here. This whole issue about taking 12 half steps in an octave and figuring out what to do with them. You might be saying to yourself, why would anybody do this equal temperament thing when you could just tune these frequencies and I don't know what you'd put in the other places, but wouldn't we want pure harmony? Yes, we would. The problem is that as soon as we start making, like, say, major thirds pure, then, well, in the case of this, it would come out lower than equal temperament. So that means some other third is going to have to be wide. If I'm going to lower the equal temperate to be in tune, then somewhere else in my scale I've made something like some other major third is going to be too wide. So this is a problem, and you could pick whatever interval you want, but usually it's the major thirds that the keyboard people and composers kind of focused on over the years. So what to do about that? So mean tone is this way of tuning that was used in the Renaissance up into the Baroque period that favored a lot of major thirds, but the problem is you just couldn't play in all the keys. So that was a problem because composers, especially from Baroque period through the Romantic, Classic and Romantic period, wanted to play in more and more keys. They wanted to use all these keys. So this is part of the reason why the movement was towards, if we just go with equal temperament, that will not be a problem. We can play in whatever key we want, and we can move in a piece to whatever key we want. We can transpose anytime we want, and it's not going to be an issue with our keyboard instruments. So, so the compromise that was occurring in the Baroque period was these circulating well temperaments that allow you to play in all the different keys, but some of them are purer than others with the major thirds particularly. And also the fourths and the fifths are adjusted various ways. But I'm going to play you the circulating well temperament called Kernberger 3, and I tuned an electronic organ from 1970. It's one of the last Allen organs that before it went digital, and I found out how to go in and adjust each pitch. So this Allen organ is tuned in Kernberger 3, and I play around the circle of fifths so that you can hear the different key colors. You end up getting these colors to each key with the major thirds and the fifths and the fourths being a little bit different than they would be in equal. And when Bach wrote the Well-Tempered Clavier book, where he wrote pieces in every single key, he had this in mind with each piece. So when you play those pieces in equal temperament, they lose that whole characteristic of key color. But anyway, I'll just let you hear the circle of fifths in Kernberger 3 on this old Allen organ, and then I will play you the last few measures of a Dudley Buck piece in the key of C major that has just about this organ on full organ, and you can really listen for that major third, because in Kernberger 3, the C to E, the major third C to E, is tuned pure. The circle of fifths in Kernberger 3. C, F, B flat, E flat, A flat, D flat, G flat, B, E, A, D, G, C. Well, thanks for listening and participating in my physics of harmony and keyboard tuning and temperament class. And I'd just like to show you a few of the books and articles that I've found very interesting to help me with this topic. Here's one by Ross Duffin, How Equal Temperament Ruin Harmony and Why You Should Care. And interestingly, Ross Duffin is not a keyboard player, he was a string player. So even string players should probably understand this problem, and I know that when they have to play with keyboards in equal temperament, they find that difficult. Somebody named Bradley Lehman came up with a temperament that he thinks Bach used for his circulating well temperaments. And no one's exactly sure whether Bach used Kernberg 3 or one of the other ones. And Bradley Lehman came up with, it's very interesting how he came up with what he thinks Bach used. And so you can check that out. Bach's air on the G string played in Lehman temperament, just temperament, which is tuning the intervals pure in a given key, and also mean tone temperament, and it's on YouTube, so I'll just put that up there. Here's an article I found, Scales Just versus Equal Temperament, and I have a URL. I'll let my videographer, who I want to thank, my daughter Teresa, take a picture of that if you're interested. This was an article I found in the Physics Teacher magazine, Teaching Resonance and Harmonics with Guitar and Piano. This was a 2014 article. This is a good book on temperament by Stuart Isikoff. If you want to actually tune keyboards in various temperaments, this is a great book by Charles Pagdam, The Well-Tempered Organ, and it gives all kinds of interesting information about each temperament that they've researched and how to tune it. And I will end by giving a shout out to our one of the mean tone, it may be one of the only mean tone organs in Connecticut, except for these electronic organs that have temperament options. But at Yale, back in 2007, they put this organ by Taylor and Booty in Marcon Chapel, which is part of the Divinity School, and it's a replica of an organ from the 1600s. I can't remember exactly where, but it's fascinating, and it can be hand pumped, or actually, sort of, I guess you would say foot pumped. You have to climb up a few steps and then stand on these huge treadles that run these bellows, or it can be run by an electric blower. It's in mean tone temperament, but to get in more keys, it has split keys. So it has A sharp. No, I'm sorry. It has A flat and G sharp, and it has A sharp and B flat, and I think it also has D sharp and E flat that are different. So when you're playing, the higher part of the note connects to one pipe and the lower part of the note connects to another, and you have to be very careful when you're playing your pieces, but you'll know if you hit the wrong one because it'll sound either much better or much worse in tune. And I just happened to have a concert program from the professor at Yale who played on that organ. So, okay, thank you.